The cycloid is one application of parametric equations. So it says a cycloid is the path traced by a fixed point on the circumference of a circle rolling along a line. And a cycloid is defined like this. So you've got your x function and you've got your y function. All right, so I know that's kind of hard to understand, so I've got a demo here I'll show you in a second. This is talking about a flexible cord with a bead on it. So if you're just holding a cord by both ends and it kind of droops down, a bead would slide kind of like this fixed point on this cycloid. But let's look at this, okay? So imagine you've got a circle or a wheel or something and you're just looking at a point on that wheel. So think about the path that fixed point takes on that rolling wheel. All right, now you kind of picture a spiral, I think, usually, but it's not quite making a spiral. So try to think about what the path of that dot is. And now check it out. That dot is making this like bunny hop pattern, okay? This is called a cycloid. This path is called a cycloid. Example 5 says graph the cycloid. So here you've got an x function and a y function, and here's where it's defined from 0 to 2 pi. So here it is right here, t minus sine t and 1 minus cosine t, defined over 2 pi. So you can see it's just this, that's all there is, but that's because that's what we defined. If I changed this to 4 pi, it's going to be 2 hops. 6 pi is 3 hops. All right, so from 0 to 2 pi is just 1 hop. That's all they want. So let's just copy that in. Obviously, for your notes, you just draw a sketch of this. But 1 hop. Notice the height of this goes to about 2 right here. And over here, 2 pi is about 6.28. Number 5, a different application. If a ball is thrown with a velocity of v feet per second at an angle of theta with the horizontal, its flight can be modeled by the parametric equations, this and this. So you need to pay special attention to these two. These are going to be important for a special kind of story problem, but this is the x and this is the y. Now, usually they're going to give you an angle, theta, to plug in there. It's going to look really super complicated, but what it's trying to describe is the path of this ball thrown by a person or launched by a launcher or something like that. Example 3 says 3 golf balls are hit simultaneously into the air at 132 feet per second. That's your initial velocity, which is also 90 miles an hour, but we're going to use feet per second, at angles of 30, 50, and 70. So they've actually got 3 different parametric equations, one for 30, one for 50, and one for 70. Notice it's xy, xy, xy. I'm using these 2 equations, but I've just plugged in the initial velocity. What was it, 132? And an angle of 30 or 50 or 70 into this place right there. Part A says, assuming the ground is level, determine graphically which ball travels the farthest. Estimate the distance. B, which ball reaches the greatest height. Estimate this height. Well, with Desmos, this is easy. I'm just going to graph these 3 things. So check it out. When you plug those in, you get kind of a weird result over here when you plug those equations in. There's the 30, there's the 50, there's the 70, but it has to do with this this boundary. So if you kick up this boundary a little bit, something weird is happening. Oh yeah, I'm in degrees, right? You've got to make sure you're in degrees on your settings. Okay, so that'll be better. 3. It's going to look like a parabola, so let's make sure and kick up t big enough to see where it hits the ground. This would be where it hits the ground, and so you can kind of see this would be the max height. This would be where it hits the ground. Let's kick this up to 4 or 5. That's not big enough. 7. Okay, that's fine. I don't need to go any farther. I'm concerned with when it hits the ground. So 5, 7, 9. Okay, fine. Doesn't really matter after you get past here. So what were the questions again? Do you remember? Which one goes the farthest? Which one goes the highest? Well, it looks like the blue one, which was the 50-degree one, goes the farthest. Let's go ahead and copy this in there. Assuming the ground is level, determine graphically which ball travels the farthest. Well, that's definitely the blue one. Estimate this distance. Okay, well, it looks like it's about, what, 520, 540, a little under 540, 538. If you want to get specific, you can kind of zoom in, I suppose, on the blue one. 536.2 or so, 536. Let's just call it 536. 536. The 50-degree golf ball goes 536, what was this, feet? 536 feet. Which ball reaches the greatest height? Well, that's the green one right here, the green one. And so that would be the 70-degree one. So we can see that height looks to be about 240. We can zoom in if we want. Yeah, 240 is pretty close. Let's just call it 240. $240 feet. Number 7, Jack launches a small rocket from a table that's 3.36 feet above the ground. Its initial velocity is 64 feet per second, and it's launched at an angle of 30 degrees with respect to the ground. Find the rectangular equation that models its path. Now remember, rectangular, when they say rectangular, all chapter long, rectangular meant x and y. So our model that we've got isn't going to be good enough because it has a t in it. You've got x as a function of t and y as a function of t. So we already did one of these in part 1 of this video series. But what we're going to need to do is plug one equation into the other. All right. So your x equation, your y equation look like this. Notice this one has an initial height of 3.36, so that's this number over here. Sometimes you'll switch this around so the negative 16t squared is in the front. I think that probably makes more sense, but this was the way it was given to us in the notes. So remember what we did. We took whichever one of these two equations looks easier and tried to isolate the variable t. So that's this one. I'm actually going to do 64 cosine 30. So, if you get a calculator and you're in degrees and you do 64 cosine 30, that's about 55.43, okay? When I write it, I round it off, but when it's in my calculator, I leave as many decimals as possible. I don't like rounding off. We want to take this equation. All I did was 64 cosine 30 was this. I want to iso the t. So I'm going to divide both sides by 55. You're going to end up, imagine if this was a 1, you're going to divide both sides. So it's basically going to be 1 divided by that 55 number. And so if you take 1 divided by that 55 number, you get about 0.018 or so. So t is about 0.018. And what we're going to do is we're going to plug that into this equation over here. All right, so 64 sine 30 is 32. You should be able to do that in your head, but 64 sine 30, remember sine 30 is 1/2. So of course that's 32. But I'm going to take this expression and plug it in for t. Okay, so I've done that right there. 32, I plug this in. T squared right here, plug that in. And just kind of clean it up and simplify. And 32 times 0.018 is this, about. And 16 times 0.018 squared is this. So you got kind of a weird, complicated looking equation. I'm going to switch these two just because I think it makes more sense to have your x squared term before your x term. But rectangular equation. You've got x and y in here. That's your rectangular equation. You should recognize that that's going to be a parabola. And that should make sense for this situation. You're talking about a rocket. It's going to be launched. It's going to fly in the shape or path of a parabola. Number 8 says determine total flight time and horizontal distance traveled by the rocket in example 7. So I think this is the hardest one, so pay really close attention. We just came up with this equation, and that was the rectangular equation for this. And this is going to be, well, it's not going to be good for flight time because I don't have a t in it. So I wouldn't use this equation for flight time. I'd use this for maybe horizontal distance. Horizontal distance is x. We should know this, right? Horizontal distance is talking about x. So if you want to find horizontal distance, you need an equation with an x in it. So it didn't ask me for max height, but I'm going to go ahead and do this. The easiest thing to do is to just graph this. So if we go back to Desmos and we graph this equation right here. Okay, we see a parabola, that's good. And what did the question ask again? Horizontal distance. Horizontal distance. So how much distance did it cover? When we look at this parabola, that's this point right here. So it's about 116.7 or so. 116.7 feet. Max height. I know they didn't ask that, but sometimes they'll ask that. And that's just going to be the vertex or the high point, 55.6 or so. Wouldn't hurt you to sketch a little parabola over here and just show your 116 and your 55. Okay. If we want flight time, then we need an equation with a t in it. Okay, so all I'm doing here is I'm taking my y component, and the y component had a t in it. So you can leave the 64 sine 30 in there if you want to, but it's probably easier if you change that to a 32. And so let's use this to find the flight time. So if I graph that, notice it's another parabola. If you look at this, oh shoot. The max height was not 55, it was actually 19. Okay, it was easy to see because both of these are the same. 19.4, so I got that wrong. Let's fix that. It's weird for a rocket to only get to 19.4 feet, but that's what this says. 19.4 feet. That's the max height. Okay, 55 would have been, the horizontal distance where the rocket was when it was this high in the air. All right, so anyway, we're talking about time. We want to know the time in the air. That's going to be this number right here, 2.1. 2.1, and that's been rounded off, so it's not necessarily exact. All these numbers have been rounded off. It's about 2.1 though. That's the time. So again, if you're trying to find time, you've got to find an equation with t in it. The flight time is going to be about 2.1 seconds. Now, if you didn't want to do it graphically, you don't have to do it graphically. Basically, for the horizontal distance, you're talking about the x-intercepts. So what you could do, I suppose, is find some sort of quadratic formula calculator. and type in those coefficients. So what were they? They were negative 16 and 32 and 3.36. Okay. Oh, that was the time. That was the flight time, 2.1. The one with the X in it was the weird, complicated one with all the decimals and stuff. So what was that? Negative 0.005184 and 0.576 and 3.36. You can't quite see it on this graph, but it comes down and it hits over here at 116.7. 116.7. So it's the same answer whether you do it graphically or algebraically using the quadratic formula, right? I didn't show you the steps there, but that's the quadratic formula. You're using the quadratic formula to get that same number, 116.7. So you could do the quadratic formula, same thing, and get that 2.1. Another thing you could do, if you found this 2.1 first, you could plug that into that x equation to find your x number. So what was x? X was this. If I plugged in, let's go back here. 64 cosine 30 times that t number, 2.1, times the time. 64 cosine 30 times 2.1 should give me the x number, 116.4. So we're off a little bit, but the only reason we're off is because it's been rounded somewhere. That 2.1 is just approximate, but there's your 116.4, 116.7. So do it graphically, do it algebraically. Either way, there you go.